Hi, good afternoon, everyone. This is Angie here. I'm from National Supercomputing Center. Thank you for joining us today at this webinar. While we wait for more participants to stream in at 3 p.m., let me just give you a quick introduction. So today, this webinar is Reimagining the Future of Smart City Planning with High Performance Computing, and it's a session that is co-organized with Ministry of National Development. Before we begin, just some housekeeping. All of you will be kept on mute by default. This session will be recorded, and you may use the chat function to introduce yourself or help ask questions between fellow attendees as well as the panelists. You may also use the Q&A function for all your questions. There will be a Q&A session right at the end of the webinar, so please stay with us. This is the agenda that we have today. And we're very honored today to have with us a very strong panel of expert speakers who will be sharing with you how they have leveraged on digital twin technology, data science, and other emerging urban planning tools to help them derive insights, drive innovation in building towards a smart city ecosystems with the help of high performance computing. They will also discuss case studies and processes of the various projects that they have undertaken. Okay, first off, I'd just like to invite our first speaker, Bernard. Bernard is our Director of Strategy, Planning and Engagement from National Supercomputing Singapore. He will be giving his welcome remarks. Then followed with, we will have Dr. Chu, who is a professor from NUS, Department of Industrial Systems Engineering and Management. And we also have Dr. Adrian Chong, Assistant Professor from Department of Building from National University of Singapore. And Mr. Eugene Xia, Managing Director from Sabana Jurong Group. And last but not least, Mr. Phil Christensen, Vice President from Bentley Systems. All right, over to you, Bernard. You may start the session.
All right, very good afternoon to everyone. Thank you so much for your time in joining us today. We are very excited to bring you this enablement session. This is one of our many outreach sessions that were conducted with our fellow agency colleagues and industry users as well as IHLs. This is one of the few that we have done this year, including one with MES, SLA, and GeoWorks itself. In this session, we would like to share with you the best practice as well as use cases on how technology, which encompass high performance computer or commonly known as supercomputers, to help you solve national problem statements as well as international issues. Okay, before we actually go into a quick introduction of speakers, I would like to thank Dr. Joning Wong for supporting and pushing restoration for this webinar, and also to Jensen and Kang Jie, I hope I pronounced your name correctly, for partnering us in organizing this webinar. And this webinar was actually gone through a few stages, including gathering topic of interest from everyone under the NMD family. And that's how we actually came out with all these speakers of your interest. Now, it is critical that as we move towards the future, which is the new norm, we want to share with you the availability as well as existence of HPC to help you enable your research and your development work. Now, having HPC is great, but at the same time, we hope that today's speakers will able to share their best practices and their knowledge and how they actually bring and answer some of these critical problem statement and how they actually bring their team together to solve some of these problems itself. So today we have our first speaker is Dr. Chew Eng Peng. He's a professor at Department of Industry Systems. Dr. Chew's current research area are in port logistics, maritime transportation, simulation optimization, and inventory management. He will be sharing with us smart digital twin for the next generation ports. Second speaker is actually Adrian Chong, okay, and he's from NUS Department of Building. He's currently leading the integrated data energy analysis as well as simulation research group itself, which engage in the interaction between building, performance simulation, real-time data, machining, and machine learning. Today, Adrian will be sharing with us integration of data science for building energy simulation. Now, one of our regular speakers, Mr. Eugene Sia. He's the Managing Director of Smart City Solution, as well as a Senior Director at Sabana Jurong. With his expertise on sustainability, digital twin, and smart solution, he'll be sharing with us on smart digital space from a township to buildings. Okay, and last but not least, we have with us Mr. Phil Christensen, the Vice President for Digital Cities, Reality and Spatial Modeling from Bentley System. He's joining us from Perth, Australia today. Phil is currently developing new ways to plan, approve, deliver, communicate changes in building infrastructure by using digital twin at city scale. Phil will be sharing more with us on shaping cities via digital twin. Before I actually jump in to give you a short sharing on NSCC, allow me to set the stage for all the presenters as well. Now, COVID-19 has done to what many government and officials and CEO and CTO found hard to do, and that is that it has accelerated digitalization, how we live, engage, and work. So government officials and business executives all have vital roles to play in guiding their countries and organizations to function effectively through the COVID crisis. The scale and impact poses a threat to a nation's survival, a business continuity in business everywhere. It has also significantly impacted every aspect of life, from a nation's competitive advantage, enterprise, economies, operation, financial system, to society and every day is reshaping the world we know. So the need to speed up digitalization for a country, for a business has gathered greater momentum and urgency. It is vital for our government agencies, local enterprises, IHL, to leverage on high technology such as supercomputing, as well as proven practices to help achieve innovation, agility, and precision. Now, I always like to share this, what I call Trinity of innovation itself. First, you need to have the idea and the data. Second, you need to have scientific talent. Third, you need to have high-tech infrastructure such as supercomputing infrastructure. By combining these three together, then we are able to leverage on the changing pace of digitalization. With digitalization, it has given birth to an avalanche of data. So the ability to make more purpose use of this data to power innovation from AI, machine learning, IoT, predictive analytics, robotics, you name it, simulation, modeling. However, we are also seeing increasing demand for computing and GPU resources to able to consume all this data and make relevant purpose out of it. So this is critical, especially if we are talking about innovation. So together with this trinity coming together, no longer are scientists, civil engineers, government officials, the need to downscale your problem. In the past, we always do sampling. Now, with good technology infrastructure, proven scientific practice, as well as data points, you were able to solve national as well as international issues without downscaling your problem. So today, I hope that we're able to give you a good perspective on what we're going to share, and we'll be more than happy to engage individually as well as a group with the NMD family on how we could support in your R&D aspects of your work, okay? Including if even if we do not have a scientific talent that you can leverage on, we will be more than happy to connect you with all the scientific talent from A-STAR, NUS, NTU, SUTT, and all the IHL as well. All right. With that, may I share with you a quick overview of NSCC and its infrastructure, so that at least you have a good idea what NSCC can offer to support in your new journey itself. Okay, let me share my screen. I hope everyone can see my screen.
Yes, we can.
Okay. All right. So NSCC, or National Supercomputing Center Singapore, is a national research infrastructure funded by NRF. Okay. As is stated here, our first supercomputer, Aspire 1, has been in operation since 2015, and our second supercomputer, which will be at NUS, will be operational by end of the year itself. The idea here is to actually provide a national resource to all national research initiatives, including IHL, RISE, and as well as the industry. Now, having a supercomputer is great, but it will be redundant without high connectivity. And I'm pleased to share with you later on greater details. The high-speed linkages that we have throughout Singapore that will have very low latency, including crunching of high GPU and CPU resources itself. Okay, in addition, we are also very well connected globally across Europe, US, Japan, and Australia. So you have international collaborators. It will never be an issue. Now, NSCC is the first national petascale facility in Singapore. As mentioned, we are hosted and managed under A-STAR, as you can see on below. But at the same time, we are funded from NRF, as you can see on the top itself. Okay. Now, our steering committee is actually chaired by Mr. Peter Ho, which is the ex-civil service head, including all the esteemed R&D and research professors from various institutions, including Mr. Kwek Gim Pugh, Professor Andy Hall, Professor Lam King Yong, and Professor Lai Chun Heng, as well as industry leaders such as Dr. Terence from Rolls-Royce itself. We also have international panels represented from Japan and US by Professor Satoshi and Professor William respectively. From NRF, we have Mr. Lim Gyok Tong. Okay. Now, our objective is really to democratize access to supercomputer. Gone are the days where supercomputers are just meant for professors or researchers. Now, we hope to actually make it available to everyone, including your government agencies as well as your ecosystem partner. Our objective is to support and drive Singapore R&D initiative, attract industry collaboration, and enhance our Singapore research capability itself. As mentioned earlier, our current system is called Aspire 1. We have a 1 petaflop system with 13 petabyte storage with InfiniBand connections. Earlier, I mentioned to you on 27 April 2021, we have awarded our second supercomputer contract, and it will be built at NUS I4 building, and it will be 10 times faster and bigger. Okay, and with this coming on board, we have definitely enough resources to support all the necessary requirements that you may have. Okay, so feel free to reach out to myself and my team. We will be more than happy to advise you and bring along the journey with you. Okay. Now, one of the key features for Aspire 2, which we are currently building, is that, as you can see here on point number 5, this is where we're going to have huge amount of accelerated computing capability with 352 NVIDIA A100. What does that mean is that with the explosion of AI and machine learning, our new machine is actually highly geared up to support all aspects of AI and machine learning. So if you are doing some aspects of these projects and work on this field, this will be coming very, very handy for all of your research work. Okay. In addition, as I mentioned earlier, we are highly connected in Singapore with 100 GPPS across Singapore. Okay, and as you can see on the map on the top left-hand corner, you will see that it's all well interlinked on that basis. So you experience low latency even you're crunching heavy amount of data. Now, especially data security will be quite a big concern for most of you. Feel free to let us know, and we actually will be able to advise you how to ensure that your research work will be all done in a very secure manner. On the top right-hand corner, you will see how we are linked to internationally to all the various countries such as Europe, Australia, Japan, and Hong Kong. Okay, and we definitely allow your international partners to access and use the supercomputer provided it's granted approval from your end as your approved collaborators. Okay, now from an NSCC point of view, we do not just stop at having a supercomputer and providing you just this infrastructure. We are constantly upgrading our natural resources, and one of the things that we'll be doing is what we call HPC in the cloud. Okay, providing high performance computing that's unparalleled, that you can actually consume on a cloud basis. Okay, and that's something that we will be talking to all the agencies very, very soon as a focus group as well as a demand pool to collate the necessary needs from all your end, so that we can actually, one, cut down your dollar spent on cloud resources, especially those that is on a heavy workload that requires heavy modeling, simulation, or machine learning. Okay. Now, the other one is basically a HPC bank. We actually are in partnership with 7 supercomputing centers across the world, including in Europe, in Australia, in Japan, as well as in Thailand, to come out with this concept of a HPC bank to allow collaborators across in different time zones and continents to access HPC resources as and when they are required on that basis. Okay, now these are some of the projects that we have been supporting in the last few years. As you can see, these are actually very important national projects. And it doesn't stop here. This is just a few. And quickly, I just wanted to share with you some of the things that we have done. Like for last year, we actually helped together with A-Star, we work on the simulation of droplet dispersion to combat COVID-19, as well as discovery of new 2D materials and urban planning for Cooling Singapore project itself. And lastly would be the genome sequencing research from 10K to 100K project itself. So these are some of the very important critical projects that we embark on, and we hope to partner NMD family as well as the ecosystem partners for future innovation and project that you may have that we can actually support you with. Okay, now I'm not good. I would like to pass the time to the rest of the speakers, and feel free to ask any question that you may have, and we'll be more than happy to share more details. With that, I end my presentation, and may I pass the time back to Angie?
Thank you, Bernard. Thanks for the introduction of our high performance computing. Now I'd like to invite Dr. Chu to join us to share his topic for the day, Smart Digital Twin for Next Generation Ports. Dr. Chu, you may start sharing your slide. Thank you.
Okay, thank you for your introduction. I'm also currently the director for the Center of Excellence in Modeling and Simulation for Next Generation Ports. And so today I will be sharing on the Smart Digital Twin for Next Generation Ports. So let me see how to share my screen. Are you able to see the slides?
Yes.
Okay, thank you. So before I go into projects, what we have done, I just want to mention that this Center of Excellence in Modeling and Simulation for Next Generation Ports is actually sponsored by Singapore Maritime Institute, which have actually given us about $12 million over the 5 years. And this center has been operating since 2018. So to start off with, I want to define what a digital twin is. And so from the slide, you can see that a digital twin is actually a digital manifestation of a physical systems. And the digital system can mimic closely to the dynamics and behavior of a physical system. So that is what a digital twin is intended to be. So of course, there are different types of digital twin. I mean, just to share with you, the most common one is actually a digital twin that actually collects a lot of data, either from IoTs or sensors or maybe through GPS. And they are usually displayed in a 2D or 3D models. There are also digital twins that uses physics model. For example, digital twin of a car engine. And this kind of digital twin will use physics theory to model the car engine. And there is another type of digital twin that uses event-based model or agent-based model. And for this kind of digital twin, it is used to model the behavior of a large system where there are many components that interact with one another. So to build this type of digital twin, it will need to capture the logic processes of these components and all the interacting activities that define these logical processes of these components. For the last two digital twins I mentioned, which is the digital twin using the physics model and the digital twin using the event-based model, agent-based model, they have the predictive power as the dynamics and behavior of the physical systems are captured. More advanced digital twin or hybrid digital twins are when both the online data and the dynamics and the behavior of the physical systems are being used. For example, here is some of the simple kind of digital twin where you just collect data and display on a dashboard, a 2D model. Like for example, this is something that you can actually get from the internet, where you can view all the position of all the planes that is flying in the airspace. Of course, I'm sure you also have heard of this DHL Resilience 360, which also created a dashboard or digital twin, which helps for their clients to manage disruption. For example, if there's an earthquake or there's a strike or there's a flood or there is some problem with the ocean shipping, then it will actually alert these clients of what is happening. And so this is a much more better digital twin because what happens is that they look into public news data, all the events that's occurring in the news, and then they mine the data. And eventually, if there's some events that occurs near their source where they need to deliver to a certain point, and if this is affected, then it will alert them. So this is some of the examples of digital twin that you can actually see out there. Okay, many people have the belief that there is only one digital twin for a given physical systems. But actually, this is not true, as a digital twin is developed for a purpose, and hence it really depends on what you want to study in the physical system. So depending on the purpose, the digital twin can have different representations from high to low fidelity model. And the reason for this is due to computing feasibility. So this is where actually the National Supercomputing Center will actually be helpful, especially if you need to draw high computing resources to run the digital twin. So for example, if we build a very high fidelity digital twin model for medium to long-term planning, then it might take high computing resources to get a solution, or it might not be able to even get an answer in time. So depending on the purpose, we build the digital twin accordingly. So in this slide, I just want to show you some example of the different kind of level of fidelity that one should use depending on the activities. Like for example, if you are looking into designing a system, right? You may not require a high fidelity kind of a digital twin, and usually a low or medium or mix would be sufficient to be able to design a digital twin for design. And for planning, it could be a medium and high mix, where you may need to actually have a medium level of fidelity. And finally, for trying to look into the daily operations, the real-time operations, this is the kind of digital twin that will require high fidelity kind of model to represent the system. So usually a smart digital twin can be measured by 4 dimensions, namely the visualization, the connectivity, the analyzability, and the granularity, right? So for visualization, it is how the digital twin presents the data in a meaningful and insightful way. Dashboard and 2D, 3D visualization will be important to display the result to help decision makers to understand and make informed choice. And we can associate the dashboard and the 2D visualization as a control tower. Connectivity is another dimension which digital twin might not be a standalone system. It may need to interface with other systems to communicate, such as receiving data and feedback and providing instructions. So interoperability is important for different systems to communicate with each other. And so because of that, some communication standards is important when we want to design a digital twin that can be able to connect to other systems. Analyzability, okay, this is another field which is important, and this has to do with analytics optimization, and is rapidly evolving with numerous optimization algorithms being continuously developed. So many existing platforms usually have simple evaluation tools without optimization. So generally, if you look into many of the digital twins that's out there, usually what they can do is just only evaluate what is happening. But they may not even have the optimization to be able to tell the decision maker what would be the optimal choice to make given the situation or the event that has occurred. So the digital twin should allow for optimization and simulation analytics, and end user to customize and embed this optimization algorithm to take advantage of the latest algorithms. For granularity, okay, as mentioned earlier, the digital twin should allow to be built with different level of fidelity, and this allows for the analysis of any level of detail required while balancing the trade-off of more processing resources required. Okay, so in C4NGP, all right, we have built an open source platform called the O2DES. It is embedded with simulation optimization technology, which our research group is very strong and visible in the international academic community. So our pod digital twin is built on top of this O2DES platform that we have actually built. So we have 3 types of optimization to be embedded in the digital twin, namely the optimization and simulation, the simulation optimization, and the simulation analytics. So optimization and simulation optimizes the best strategy to be used. Simulation and optimization helps to identify the best design configurations, and the simulation analytics helps to give the best decision in real-time operations. So the digital twin will be supported by visualization, such as dashboard, to give insightful information. In addition, we are also creating a PodML, a universal markup language that specifies the pod configuration. And with this PodML, it can help to accelerate the model building of the digital twin. So we illustrate how our O2DES platform have helped to support the pod digital twin. So for example, in optimization and simulation, this usually occurs in operational setting. For example, when an event occurs, such as when a vehicle or yard crane completes a job. So where should it be assigned to next, or what task should it be assigned to? And so an optimization model can be called to provide decision which job should this vehicle or the yard crane to be assigned to. So in this example, we can test out the effectiveness of the fleet management system. Instead of testing out the fleet management system in a physical space, which can be very disruptive, it can plug into the digital twin to assess the performance of the system. Okay, for simulation optimization, this is usually for finding the best design. So for example, in the new pod concept, the digital twin can help to find the best combination of resources to meet the throughput target. In this case, addressing what is the right layout to use, what is the right number of yard cranes, key crane, and vehicles to deploy. Okay, in the next slide, this is an example of our digital twin being used to help to look at one of the pod design configuration for one of the fingers in TWAS. You can imagine that the size of one finger can be as large as 4.4 kilometer by 1 kilometer. And so it is a large and complex system containing a lot of events and activities. Here, we show our digital twin is scalable and runs decently to get the solution. One of the opportunities in having a digital twin is in the area of simulation analytics. This is particularly important in the real-time decision-making where we need to make a quick decision when an event occurs. Usually, when using a sophisticated optimization model to get an optimal solution will require long computational time, which becomes impractical. So to resolve this issue, we use machine learning with the help from the digital twin. In the physical world, we are bounded by space and time, and also by the type of data we use to learn, usually the historical data. But historical data only limits us to, to make good decisions when such scenarios happen again. But when scenarios have not happened, then the learning model might not be able to give effective decision. But in a digital twin environment, these boundaries can be relaxed, and we can perform many different types of scenarios, which some of them have never happened before. If the digital twin has this predictive capability, then we are able to predict accurately the output for any scenarios that have not occurred before. So with this digital twin, we can learn not only from the historical data, but also from generated data or new data or scenarios that have not happened before. So in short, the digital twin can help us to anticipate and hence able to help us make better decisions when such scenarios arises. The key idea, okay, is to map the scenario space to the optimal decision space. So when an event or scenarios occurs, with the learning model, it will be able to quickly tell what decision to make. So by using a simulation analytics in a digital twin environment and connected to IoT sensors and terminal operating system, the digital twin will be able to work hand in hand with the physical system to help the next generation pods to be efficient and intelligent. For example, the digital twin can be used for disruption management. Suppose there is a vessel accident that will cause the capacity of the sea lane to reduce. So the digital twin, given the real-time information on the system state, it can play out in fast time how the accident will impact on the port operations and when the hotspot and where the hotspots will occur. With this predictive power, the decision maker can come up with good strategy to mitigate the hotspot even before they happen. So this slide shows some of our projects that we have involved in. Many of our projects are developing solutions to address the challenges faced in the next generation ports, especially in the TWAS new port that is being built. The projects cover designing and optimizing the new layout of container port in TWAS. For example, finding the right number of battery charging stations and locations, identify robust transponder locations. And in the operation strategies, we look at AGVs deadlock detection and prevention, AGV battery deployment strategy, and storage yard management strategy. We also look at the maritime ecosystem, which interface with the ports, such as the traffic impact analysis on the land transfer of container between the Pasir Panjang terminal and the Tuas, and the collision avoidance advisory system for the sea channel. All these projects which involve modeling and optimization are developed using our digital twin platform. So here I end my talk, and this is where my center is located. It's in NUS at the 3 Research Link, and so in future, if you like to, if we are able to permit for a visit, right, please write in, and then we'll be able to give you a tour. Thank you very much.
Thank you very much. Thank you, Dr. Chew, for your insightful sharing. Now I'd like to invite Adrian to start his sharing now.
I hope you all can see my screen.
Yes, we can.
All
Thank
right.
you.
Very good afternoon. My name is Adrian Chong, and I'm an assistant professor at the Department of Building, and starting next week will be called the Department of the Built Environment at the National University of Singapore. So as you know, this afternoon, I'll be discussing the topic data science for building energy simulation. And what I'll be doing is basically sharing some of the findings and ongoing developments at my research group. So data science, as you all know, is an interdisciplinary field that combines, domain expertise, processes such as data preprocessing, as well as algorithm development. And the whole point of doing all this is to extract meaningful insights from data. So it is the same with building energy simulation or building performance modeling. What we want to do is, through a combination of domain expertise, processes, and algorithm development, extract meaningful insights from our models to aid the decision-making process. So let me first introduce my research group. We call ourselves the Ideas Lab, which is the acronym for Integrated Data, Energy Analysis, and Simulation. So our research focuses on various aspects of building performance simulation, including uncertainty quantification, model calibration, and building data analytics. So a lot of our research focuses on creating energy efficient buildings. So you can find out more about my research group by scanning the QR code. And I also like to take this chance to acknowledge my postdoc research fellows as well as PhD students, without which a lot of the research would not be possible. All right, so in the next 13 to 14 minutes, I'll first present how we enable this integration between data science and building energy simulation. Then, due to limited time, I will illustrate one specific case study or application, which is the use of building data science in building energy simulation using model calibration as an example. And then finally, I will summarize the free and open source toolkits that we have developed and what we are currently working on. So before we begin, it is important to recognize that there are many existing whole building energy simulation software tools. So I did a quick search in the building energy software tools directory, and you'll see there are currently 207 software listed. So however, the issue is that the workflow between running energy simulation and data science is often not streamlined. So I give you an example. For example, I could download building measurement, building data, and I'll be processing it using, for example, Excel. And then I might be updating the model on Energy Plus or its interface design builder. So for those of you not familiar, Energy Plus is basically a whole building energy simulation engine. I could be using, an application software called JE Plus for sensitivity analysis. I could be using R and Python to do, create meta models or deep learning models, using deep learning algorithms to create meta models of energy simulation models so that I can speed up the computation. And there's also another tool called GenOp, which is very famous, in the discipline to which we use for optimization. So as a result of this need to switch between algorithms and platform, we believe that this would deter the use of data science, certain data science techniques or methods. You have to spend a lot of time processing the output from one tool or software so that you can input it to another. So, and also very importantly, right, methodologies that involve constant switching between algorithms across multiple platforms are often harder to reproduce. So in one of a recent literature review of calibration papers that we found that, we review 100 papers and almost all of them are not reproducible or very, very difficult to reproduce. So to aid this application of data science to building energy simulation, so one of my postdocs developed an R package. So this is called E+R. So the R package consists of two components. The first is an input-output processor. And what this basically does is that it structures the inputs and outputs of the energy simulation for seamless integration with existing data science workflow. The second is a parametric manager component that makes it easy to run large number of parametric simulations. You can imagine you'll be able to evaluate different climate change scenarios, like run thousands of simulations, especially with the support of HPC. So what do we mean by structured model inputs and outputs? So first of all, a relational database is used to represent the simulation model and weather file so that the relationship between different model inputs are maintained. Secondly, object-oriented programming is used to enable better code reusability as well as flexibility. And third, the R package organizes the simulation data in a tidy format. So for those of you who are not familiar with R, you probably do not know what tidy format is. So tidy data basically refers to a consistent way to organize data in R. And it's based on three very simple rules. You have variables in your columns and observation in your rows and values in your cells. So it sounds very simple, but the reality is that a lot of modules, a lot of code do not use tidy data for input and output. So making a lot of data science workflow disconnected. So the key advantage would then be, once your model inputs and outputs are in a tidy format, you can take advantage of all of R's data transformation and visualization capabilities. They are actually designed to work with what we call tidy data. And what this means is that, you will be able to quickly reduce and analyze large volumes of simulation data. And then you can focus your analysis on the most relevant data. So for example, imagine you have a simulation output which has thousands of variables. You can quickly, select certain variables that's of interest. You can filter them to a certain time period. You can arrange them or sort them in a certain order. You can transform them, perform operations on them. You can group and then summarize them. And, you can also visualize them very easily once your inputs and outputs are structured. So the second component, as I mentioned earlier, is the Parametric Manager. And what this does is that, this component provides a set of abstraction that makes it easy to basically create many parametric models to evaluate different design alternatives. And once this is done, you'll be able to run them in parallel. So you can imagine, you'll be able to set different parameter values and easily run parametric simulation of thousands of simulations. And because all the simulation data are structured, it becomes very easy to map, consolidate, and work with data from multiple simulations. And then later on, after it is consolidated, as we've shown previously, you can then visualize and analyze the data. So now that you're aware of how we can interface between building energy simulation and R, let's move to an example application of data science to building energy simulation. So I will use the automation of model calibration as an example because it involves working with both measured and simulated data. And the workflow for automated calibration of building energy simulation normally involve switching across different platforms for data processing, sensitivity analysis, calibration, as well as the evaluation of your model performance. So with the E+R package, as you can see here, we'll be able to easily extract and map relevant model inputs and outputs to the measured data. You can use things like regular expression, and if your data is structured and labeled well, you can easily map them. So this is followed by the use of the parametric module. So what you can take advantage of the parametric module to explore different values of model parameters and how they relate to the model outputs. And over here, what we do is, we apply Bayesian calibration to find the set of model parameters that provides a good match between the model predictions and the actual measurements. So Bayesian calibration can be thought of as a calibration under uncertainty, where we use Bayes' theorem to quantify the uncertainties in the parameters and the model as part of the calibration process. And like all Bayesian processes, is extremely slow. So it takes a lot of time. So what we usually do is we can do downsampling to speed it up. But now with HPC, of course, this is something that we want to explore as well, to see the capability to use the full data set and whether, how long it takes to apply Bayesian calibration and investigate its scalability. So like all our other developments, the code for conducting Bayesian calibration is open source and based on RStan, which is basically an R interface to the widely used probabilistic programming language Stan, which is written in C++. So, I mean, a lot of details here, but the key takeaway is that, we are now able to carry out this iterative process of data mapping, data pre-processing, data processing, model calibration, and finally, the evaluation of the model in a single streamlined workflow. So with a streamlined workflow, we can also take this a step further. We can continuously update the model towards creating a digital twin that stays relevant over time. So this work is part of a research project where we propose a framework that continuously use the time series data from the building management system to update the model. And through a Bayesian approach, we are able to retain what we learned from the previous model to the next, the newer model, the updated model. So we believe that, continuous model updating is becoming increasingly possible as data becomes increasingly available due to advances in sensing and IoT. And it's also going to be increasingly accessible as querying data via, a web-based API becomes a norm in the specifications of building management systems of the future. So what we do here, what you see here is, basically for this proposed continuous Bayesian calibration framework, we use 3 years of measured data to compare the non-continuous approach, where basically we calibrate the model with 12 months of data, and we look at its performance in the subsequent 2 years, 24 months. And then, we have a continuous approach which we compare against, where the model is recalibrated every month. So if you look at the box plot on the right, our findings indicate obvious improvement in model prediction, where you see a smaller error with the measured data. So prediction over 2 years of test data set using the non-continuous Bayesian calibration, the non-continuous approach, show larger prediction uncertainties, as you can see with the yellow box plot, as compared to predictions with the continuous Bayesian calibration, the blue box plot. So the red points are the measured data. So additionally, what you can notice is that the non-continuous calibration tends to underestimate actual values, with most measurement falling, above the third quarter of the box plot. So basically, what happens is that, the continuous approach keeps the model updated so that there is less bias. So this observation of reduced bias can be attributed to the use of more recent data, basically in the model calibration effort. So not surprisingly, we also found that, basically this moving from left to right is, in calibration model, basically what we are doing is we are estimating the parameters of our model. So what happens in this is that, we found that, as you continuously update the model with more data and more recent data, you also become more confident of the calibration, as illustrated here with the decrease in the posterior uncertainty, basically the uncertainties in the estimated parameters over time as you move from left to right. So with this, I would like to encourage all of you to take a look at our free and open source developments. So in this presentation, I talk about the first two, which is E+R and Bayesian calibration. Both are open source and freely available. So unfortunately, due to limited time, I am unable to introduce another one of our R packages, which we recently developed, and I thought might be interest to some of you. So it is our EPW Shift R, which you see in the third point here. So what this R package does is it basically creates climate change projection weather files for energy simulation based on the latest IPCC assessment report 6. So the reason this came about was basically, we wanted to, we were working on evaluating different climate change scenarios, and we were met with this huge roadblock of, purchasing climate change weatherfall that is very, very expensive. And, there are many scenarios, so the cost can scale up very quickly. And being researchers, we don't have that kind of money to spend on weatherfalls. So both E+R and PWShift are also available on, on GitHub as well as on Crane. Crane is basically a repository for storing the latest, it's a global repository for storing the latest R code and documentation. So if you think all of this is great, but you do not know where to start, so I am currently writing a book called R for Building Energy Simulation for my class at NUS. And the book will be written using R Markdown, and it's intended to provide documentation containing code. So basically, it'll show the reader how to perform data analytics and use algorithms such as sensitivity analysis, optimization, and Bayesian calibration. So I plan for it to be ready soon, and I will inform those interested via email when I post it online. And before I end off, just some what we are working on now. Open source web-based visual programming interface, we are working on that. It's going to be a JavaScript package, so anyone can develop their own visual programming interface. The other thing is, we are working on this high-quality open data set using the SimbaBest testbed located at Create. So there are a lot of building data set, but there isn't a high-quality open data set with a high-fidelity open model, so that when anybody claims that, my digital twin is really good, we have something to benchmark against. And with that, I end my presentation. Thank you.
Thank you. Thank you very much, Adrian. Next, I'd like to invite Eugene to start sharing your presentation now.
Right, thank you, everybody. Can I confirm you can see my slide?
Yes.
Right, based on the timing, actually, I should be finished speaking already. But I'll probably spend the next 10 minutes to quickly go through what I have in terms of smart digital spaces for smart cities and how we use digital twin. And then probably we have some Q&A. Slides are made available after the presentation. So basically, when you look at a digital twin for smart cities, you really have to have a framework. And the framework that I follow is 37100, and it's an international standard. That's where it looks into things like social equity, feedback, saving of utilities, safety, the happiness or delight factor, and sustainability. So I've just got a 7-point agenda very quickly on what are the touch points that we use and how does HPC come into play, how digital twins come into play, as well as in terms of all the analytics. So very quickly, we have a platform called 24K that not only data ingest information, it also can display it in an integrated operational center. It has its analytics layer and so on and so forth. It's been around for some time, and there are about 26,000 lives that's being monitored using this. And it's really a great tool because from the same tool, we are actually doing our own pandemic management platform. We are coming out with our own integrated facilities management and with Omni, for example. So it's really a common data environment that we use. Thousands of sensors can come onto it, and that's the reason why HPC is actually needed, because we have a plan how to work on how today, just a couple of half an hour ago, there's been an announcement of how we are putting 3,000 worth sensors in Temasek Poly, all going through the system so that we'll be able to look in terms of creating a good, nice well-being. So those two things you see here is able to go into our CDE and able to generate reports, as what Prof actually mentioned. You need to be able to optimize it, and from the report, you'll be able to analytics layer will be able to tell you, hey, these are the ways that you can actually look at it, what may have gone wrong, and best, even predictive and preemptive maintenance. This is what we're actually doing in some of our clients now with smart lighting, access controls. We have also equipped our own offices with this. Happy to invite you guys into our collaboration hub to have a look, which includes security, people counting system, pandemic management, sound sensors, circadian lighting, and so on and so forth. we look at, so long as the asset is able to give a signal, we are able to monitor it. And but that's where, again, because once we get too much the signals in, what do we do with it? How do we analyze it? How do we simulate it? How do we optimize it, the either workflow or the in terms of the physical assets. So these are some of the things that we monitor real time, and we bring it into our platform. And there have been savings. I mean, there are savings for town councils, there are savings for our clients locally and also abroad. And the best thing is all in clouds. We are able to look at lift operations. Apologies, I have to blank out certain things because and able to know who are the good suppliers, bad suppliers, what are the chronic lifts, what are chronic assets, for example. And all this is able to give good information to people running town councils, people running cities, people running buildings, and it's all real-time information. And guess what? We have also now working with our landscape architects in SJ and providing, even knowing whether the soil is okay, good or not. Trees are actually leaning. You have those landscape sky gardens, and trees are, have a possibility of leaning. And we'll be able to preempt, knowing the soil, oxygen in the soil, microbes in the soil, are they okay? Are they at a good level? So that we'll be able to know about how we can maintain the flora around the area. Dashboards. So we do have this whole digital twin that we have created. There are two types we are looking at. One is actually really a scan of the building, and another one is from a BIM model. So I'm just showing you a scan, a 360 scan, and really we'll be able to come out with happiness index at a glance, whether people are happy or not in that area. And we are going to be building our integrated command control center in our new campus. We're able to show all these and even work as a crisis management center in the future. So this is what our future we envision, whereby in the campus, this is what we'll be doing, and things like not only on sensors that we are going to be monitoring, FCC, fire, and also overseas. And our clients are from overseas are actually saying, hey Eugene, can you also monitor my sensor, my assets over there? I'm getting reports that it's working very well, but it's actually breaking down half the time. Can you monitor it? I say can, because why? We can have a digital twin of your place in our system. We were then able to do that monitoring in Singapore and send the data, because everything's on the cloud right now. We have our own system for using BIM, and like what Prof actually mentioned, we are actually working with Autodesk, with Forge, and we'll be able to take in the ingest, the BIM model. We are truly following what BCA is saying on the IDD, whereby data from the design stage goes into the DFMH, the design for manufacturing assembly, to the construction, and exactly what we are doing now in terms of the operational and management. So I think we're a very unique position that we'll be able to look at the entire system and also have a workflow that comes together with it. We're talking about facilities management and asset management. So this is really something that we have actually rolled out this already. We are going to be having it for our campus, and with the new IFM tenders that are actually coming out, very happy to actually put this and to all the GPEs or agencies that are in here. Feedback, the triple bottom line in sustainability, right? You've got the people, profit, planet. So the people, to me, is one of the most important ones. So in terms of getting feedback, dilapidation surveys, tenant feedbacks, we do have a portal that's able to, a platform that's able to take this feedback in and look at how the building, the space, and also even the precinct or even the city is looking at it. And it all boils down to ISO 37100 again, that there is a requirement for data analytics. And again, something that we are actually benchmarking to international standards, taking feedback into consideration on where, for example, the hotspots are, and cross-reference it to whatever data we do have, because some of it is still kept with the government. We don't have visualization on it, but what we do is people's feedback. People's feedback counts. and we'll be able to know how the sentiment, and we talk about sentiment mining. We're talking to some IHLs this morning where we are able to provide this sentiment mining to know where the students at risk, for example, and how we can identify these students at risk early before they actually drop out or worse, commit suicide. So these are the things that we are very proud of in terms of our data analytics. We have 6-7 guys that looks into this to see how we can improve the quality of life in the cities that we design, build, and manage. All this comes into this system called the Integrated Estate Management System that Sabana Jurong has, and this is something that we are not only marketing it in Singapore but overseas as well in the new projects in, for example, in Jakarta, in Vietnam. Soon we're trying to pushing it to Malaysia as well, because why? These are all the benefits of wastage, less wastage, reduce labor, and you know what? Singapore is moving towards sustainability. So this is whereby we sensorize a nation, able to put it back into a brain and get all these into a digital twin of Singapore, and we are able to manage all these. I'm a QS by profession, and I'm very interested to see how we can get good contracts, good pre-qualification of the tenderers, of vendors as well. So all this goes into a system we call the IEMS that is it's available now. We're using it in Singapore, but again, this goes into a building space or a small space where we have actually put all these sensors and this program into a 400 meter square space that is a brownfield building, and so we have proven the point that it doesn't need to be a greenfield buildings. Even the brownfield buildings out there that are they are not in BIM, for example, we can BIMify it, sensorize it, and we even if it doesn't have a BMS system, we go in and create a digital twin enabled with HPC analytics inside. Last but not least, we'll be able to look. So Prof also talked about in the design stage about having a digital twin. So this is a same case where we do a digital twin in design, and this is exactly what will take a couple of weeks to carry out lightning studies. For example, we are doing it in a couple of minutes. Because of time, I'm going to fast forward this. As you can see, it's only like 1.5 minutes, and we'll be able to come up with a net of the building on lightning protection. Right? So this is one of the innovations we're doing, and that's the importance of digital twin. But this type of analytics, this is one building, right? And that's the reason why HPC is needed. I'm actually speaking with Tommy and the guys on NSCC said, hey, I think I need more processing speed, because when I need to do more iterations for my clients, I cannot be waiting even in the cloud. I need them to come in to help me to make me more productive, giving my client more value by producing more of these iterations or options for them. So this means that we can look into producing green guidelines in terms of guidelines for modeling. Well, ConnectX is coming, so guidelines for modeling for good BIM, so that the model checkers that we have will be able to look into that and ingest the data, and even drones. So this is something that we are looking at with our partners, even to flying drones in the culverts. What would have taken weeks to do into checking on the integrity of the buildings, we are actually doing it in hours. We have given this back to our landlord, and they know where are the areas that, and we run it through an algorithm to be able to pick all these up. And our partners are this Aero Lion, and able to produce all these. So I'm going to move quickly to conclusion, right? And so all this is really looking at smart digital spaces. Spaces can be as small as a 400 meter square place, a building, a precinct, a city, a township. And that's where we are looking at to see how we can really improve quality of life, be sustainable, right? I remembered, I think some townships are coming together to have a sustainable plan, be sustainable, and most importantly, with the reflection of data. This is what we have done for Singapore. We'll be able to look at some part analysis, cameras, open data. This is we feed it to our lifts, so we can know how all the lifts are actually working with the GPS coordinates, agent infrastructure, how, for example, energy efficient of the buildings are, all the way to even flooding, for example, where we are doing simulations with the SJ NTU Corp Lab. That's all I have to share. I'd like to thank you, and I'd like to hand over to the organizers. Thank you, Andy. Sorry for speaking so fast.
Angie,
Yes.
Bernard here. Can I just add? I also want to share with the rest of the attendees here is that we are actually exploring with Sabana Jurong to see if there's a possibility of making 24K their digital twin available on NSCC supercomputer. So if that works out, do look out, and that's something will probably would be a great benefit for Singapore.
Thank you, Bernard.
Thank you. Okay, last but not least, let us invite Mr. Phil Christensen from Bentley Systems to start his sharing. Over to you, Phil.
Thank you very much. Can I just do a sound and screen check?
Yes, we can see your screen and we can hear you well.
Hi, everyone. Thank you for attending. And last but not least, let's talk about how we can work with digital twins at city scale to shape the fabric of the city. Quick introduction to Bentley Systems. We're a large software company, 4,000 people in 60 countries, and we specialize in helping engineering firms, owners, and cities to design, build, and maintain the infrastructure of the world. And we're very active across all the infrastructure types you see on the top right here. And of course, they all come together to build our cities. I'm going to talk about 5 technology trends which are driving a really fundamental change in the way that we model, simulate, and change the physical fabrics of our cities. Tech driver number 1 is there is an explosion of spatial sensors underway. Every month, every week, I get an email in my inbox about a new kind of sensor, and they can capture the world in many different ways. They can take photos, they can take panoramas, they can generate meshes, they can do laser scanning, they can do multispectral scanning at different wavelengths. And it's extending down into consumer devices. The latest iPad Pro and iPhone 12 have a laser scanner built into the device that allows real-time 3D reconstruction of the world around you. And we have users in production who are using that already, and we're managing their data for them. So these sensors let us capture the world in ways that we've not been able to do before. Number 2 is an explosion in autonomous vehicles. So whether it's a CubeSat, which is a small satellite, autonomous long-range drones, small consumer-level drones, autonomous robots, of course, self-driving vehicles, and even autonomous vehicles like boats for marine mapping. There are a whole range of different platforms. These are all products available today. This is not the future. And so that provides an amazing platform. If I use the example of CubeSats, if you go to planet.com, you can buy imagery of every place on the terrestrial world updated 3 times a day using this new constellation of small satellites. So they're great platforms for mounting these sensors. Tech driver number 3, our host today, are the expert in this, and that's high performance computing. And the big change there is the increase in parallelism, whether that's in cloud computing or whether it's on premise. And so it really gives us unprecedented scalability to attack problems by using very, very scalable compute, a lot of compute nodes in parallel, super scalable storage, which can be scaled just about infinitely now. And of course, not to be forgotten is scalability and communication, the ability to have a lot more communication, not necessarily with people, but with a lot of other devices and other distributed compute facilities. Our tech driver number 4, GPU processing. So for those of you who are not so technical, in your computer, you've got 2 types of chips, the central processing unit, the CPU, which does most of the calculations, and the graphical processing unit, the GPU, which is the graphics card that's probably used by your kids for computer games, but it's now being applied to machine learning and many other compute-intensive activities. So GPU processing is a very big deal and a really big change. And I'd just like to play a video for you. This is a video of a truck driving down a road, except it's not a video. This is a completely synthetically generated scene. It's generated in real time. It's not pre-computed. And you can see the suspension of the truck moving, if the trees and the grass are moving, if the wind is blowing. Everything in this image is synthetically generated on a GPU in real time. So it gives you some idea of the performance capability of these new types of chips. And tech driver number 5, artificial intelligence and machine learning. A number of our presenters have already mentioned this today. This is doing it at city scale, where we start out with a very detailed 3D model. This is not a photo, it's a model. And here we're automatically classifying all the different parts of the city in different ways by using machine learning that's been trained on a lot of aerial imagery and a lot of the derived artifacts from those aerial images. Again, this is not a video, this is a generated 3D model from previously captured photos. So then we can bring that into the design environment. Here we have the design environment where we bring in that 3D city model, and we use the classification that's been performed using machine learning to then guide the city planning decisions. We might extract center lines and features out from the city. We can extract a terrain model from the city. There's many different applications that can aid the change in the urban fabric. And we can even combine different data sources together, satellite photography with the terrain model, to give us an interactive design environment. And so each of those 5 technology drivers by themselves would be a very significant change, but in fact they all combine together. So the sensors can be mounted on the autonomous vehicles, they deliver data to our high performance computing infrastructure, and in that computing infrastructure, the GPUs running machine learning algorithms deliver new insights to us about what's going on in our city and what some of the consequences of change might be. So that's the technology landscape and some big things that are happening. Let's take a look at how does this drive what we can do with an urban digital twin. So first, a quick definition. As others have said, it's a digital model of a physical city, and it combines together many, many different layers of data from many different sources, from IoT and operations to engineering to surveying and so on. And why do cities use it? We have about 60 cities that we're working with. Why do they use it? On the top right are some of the use cases where they're finding value, whether it's making development approvals faster to attract investment. Definitely climate change and resilience is a big area where these models are being used. Security, of course, always important. The reduction in siloization of data. This is a massive issue for all cities and governments. Separation of data between departments, between government and citizens. A city digital twin helps to bring people together in a common environment, and one of those applications is citizen engagement. So out of those 60 cities, I just decided to pick 3 examples of cities we're working with that with some different interesting use cases and really what we've learnt with city digital twins in action. So where you all are today, just up the road from me in Singapore, I think what we've learned there is that, you know, you can try and do a big bang approach to a city digital twin, but really the digital twin needs to evolve with the physical fabric of the city as it evolves, and therefore it's an evolutionary process, project by project. Every time a project of any time changes the city, that should be connected in with the evolution of the city digital twin, and we're working with LTA and BCA and others on that type of approach. And in Singapore, you have a particularly interesting underground infrastructure that's expanding, and we've done some interesting work there and in other places. And often a forgotten part of digital twins is what's going on underground, and that's a big area of interest for us, and we have a lot of capability there. Dublin, interesting older city. The pre-COVID major events were a very big deal for them for visitor attraction. And they hope that that's going to be part of their COVID recovery plan as people start traveling again. And they use their city digital twin for planning major events. They're also very much into open data. And so rather than just having open data be downloads of Excel files or CSV or cryptic APIs, they make the open data available in the context of the city digital twin. It's very consumable. And then finally, in Stockholm, we have quite a few users in Scandinavia that are very progressive in citizen engagement, and some tremendous use cases about engaging with citizens using the city digital twin across a range of different devices in the web browser, on a phone or a tablet, and on a large touchscreen. And they're particularly interested in proactive and climate change, both reducing their own city's impact on climate change and doing traffic simulation and energy analysis in the digital twin, and also mitigating the effects of climate change through flooding simulation and resilience. So I'd like to conclude by just showing you all of this in action in one place. So this is our digital twin platform environment. We use the brand name iTwin for infrastructure digital twins. And we start out with a city scale model. As I mentioned before, this is not a video. This is an automatically constructed 3D model from a combination of helicopter, drone, and drone-based photography. Ah, dear, sorry about that. I just went to the wrong, pressed the wrong button. Just bear with me 1 second. Sorry, let me zip through. Okay, there we go. Apologies for that. We then go from the 3D city model that's been created automatically to overlaying engineering and architectural information about proposed developments, bringing in information from a range of different organisations, doing simulations on lighting studies and energy, overlaying other types of data such as economic data about what's going on in districts across the city, managing a portfolio of projects of how the city physical fabric is changing project by project, including underground data by making the top transparent, and finally, crowdsourcing information from citizens. So this is an example where the digital twin app is used by citizens. They log their comments and suggestions around the city, and they're brought together in one place for review and reporting. So the city scale digital twin, we think, is going to be part of every city's future, and we're looking forward to working with many more cities on this. And the evolution of the technology here is clear, and the role of high performance computing in managing all of this new type of data is self-evident, I hope. So I'd like to keep my presentation short and sweet today. Thank you very much for listening, and back to our presenter.
All right. Thank you so much, everyone, for your time. I know we overran, so now it's actually a Q&A. But we do have a few people who actually submitted some questions, but we may not be able to go through everything. My apologies, but we definitely will be sharing all the presentation stack with you, decks with you. Now, maybe allow me to slip in two questions just to take up another 5 or 10 minutes of your time. The first one is for Dr. Chew. The question is, how applicable is your research to replicate what you're doing for smart building and cities, especially for the southern waterfront development?
Okay, just to take a question on that. So essentially, we look at our digital twin, right? Our digital twin is mainly for operations and optimization and how to the operations. So if you're talking about infrastructure development, so what we can do is actually, like, for example, if you have certain infrastructure, we'll be able to accommodate the kind of traffic flows, and things like that. So this is some of the ideas that we can actually contribute when it comes to infrastructure development. So for a given, let's say a logistics network that you want to look into whether this particular logistics network is efficient, whether there is congestion, whether it will pose certain hotspots. This is where actually we can actually contribute to this thing. And also we can also look into traffic as well, because for example, if you know about traffic flows and things like that, you can actually transform the kind of, because there's certain standard formula where you can transform the car that is moving. And based on that, you can actually transform into the carbon footprint that's being generated. So at a system level, the digital twin will be able to actually measure those kind of things. So it's some of the examples that I'm just that are given a certain infrastructure that you have, depending on what you want to study. For example, you want to study in terms of carbon footprint, or you want to look into the traffic flow, efficient or not, or when you set a certain new activities into the infrastructure, right? This actually cause any bottlenecks or some of the problems that might occur. That's what we can actually do for this kind of studies. Like for example, one of the good examples is what a project that we have done. Like I mentioned about, we put in the traffic impact analysis between the containers that's flowing between Pasir Panjang port and the Tuas terminal, right? So this situation, right, because the Tuas terminal will only be fully operated in 2040. And so before 2040 to 2040, right, means now to 2040, there will be transfer of containers between these two ports. And so this will eventually overflow into the public roads. And so given this kind of flow or the flows that's going through between these two ports, how will it actually impact on the public roads? And so this is something that we can actually look into, for example, getting LTA data on the existing condition. Now, of course, we have to do prediction on future volumes, what growth in this thing. And based on the road network that the container trucks is moving across, then we can look into certain potential hotspots and let's say that more traffic generated from there.
Okay. All right. Thank you, Dr. Chew. Now, the other question I think is for Eugene. For Savannah Jurong, do you have similar energy optimization integrated within your digital twin as per Adrian's sharing with approach from data science?
We do have simulations because we do it for buildings and also for cities. But in terms of data analytics, I must say that we are falling a bit short on that. Because what we are looking at the data analytics is on in terms of smart cities, in terms of facilities and asset management. But that doesn't mean that we are not going to go into it. In fact, there are some discussions. I think we've A-star before on see how we can go into it. But there's actually a balance because one part of it is that the clients they want to see actual simulations and actual results, whereas the other one is more of a predictive thing that we trying to look at. So we are trying to find a balance over there. Whereas in terms of FM and AM, we want to know the predictive because we want to make sure that safety, right? If we know that this lift is going to be spoiled in two weeks' time, let's go and repair it and don't wait till someone is trapped inside or someone trips and falls and have some issue. So there is actually a balance between the two of them.
Okay. Maybe it's also good to use Adrian's model.
Yes.
And
I just texting Adrian and say, hey, we better get together.
Okay, that's good. All right. There are three other questions. Unfortunately, we ran out of time. I do not want to take up any more of the time for the attendees. With that, I would like to thank everyone for your precious time that you spent with us. I really appreciate it. I've actually posted my mobile number please feel free to WhatsApp me. If you have any question regards to the scientists who have presented today and you like to connect with them, or you like to see how HPC can support all your research project, feel free to engage myself and my team, and we will be more than happy to discuss in details with you. Okay.
Yep, we do have thank you, Bernard. We do have a question from one of our attendees, Penny, on her question on the approach of incorporating digital twin into infrastructure design and planning. So because Penny, we are a bit short of time, we'll get the speaker to answer the questions and send it over to you. Okay. So
okay.
Yep. So before we end, so I also like to invite everyone here, if you have further questions that we may not be able to address at this session, please feel free to make use of our post-event survey form, where you can put in some of your questions, areas that we haven't get to answer. We will get the speakers to answer them and send it over to you. You may also from here request for a copy of the slides that's been shared today, or if you are very interested to explore how HPC can be of use to any of your research or any of the projects that you are working on now, feel free to also use the form there to request for more information and how to start assessing. We'll be more than happy to help you with this. Thank you everyone for joining us today.
Thank you, Angie. Thank you for the
and a big thank you to
invite.
all the speakers. Thank you very much for your time and insightful sharing.
Hold on, somebody's answering the question. Dr. Chiu is answering the questions to Penny Kong.
Oh, no, it's me. It's me.
Okay.
Okay.
And
all right.
Christensen also. Thank you very much, everyone.
Thank you.
Thanks, everyone. Bye-bye.
Thank you. Bye-bye.
Bye. Thanks, Bernard.